Hey everybody, Dr. Retzek here. This is our first video for Chapter 15. It's a fresh start. We're going to learn all about integration for functions of several variables. Let's get started. The key thing in Chapter 15 is to maintain an analogy between what you learned in Calc 2 about integrals and what we're going to learn now. It may be helpful to start with the analogy that we cultivated between Calc 1 and Chapter 14. So I believe the analogy went something like this. Sometimes you have a picture that's for Calc 1, and sometimes you have a picture that's for Chapter 14. In Calc 1, the classic Calc 1 picture is like this. Good old XY coordinate system, y equals f of x, some sort of a graph in the xy plane. And in Calc 1, you learn all about tangent lines. So the derivative tells you the slope of the curve, and you can use that idea to solve all sorts of Calc 1 problems. Likewise, in Chapter 14, we have not a curve, but a surface, z equals f of xy. And that's sitting not in 2D space, but in 3D. And we go to points on that surface and we compute not tangent lines, but rather tangent planes. And we can use those tangent planes to approximate the surface. That's what happened between Calc 1 and Chapter 14. Now let's redraw the analogy. Only this time, it's an analogy between Calc 2 and Chapter 15. All right, classic picture in Calc 2. Good old XY coordinate system. Some function y equals f of x over some closed interval a to b. And we're interested in the area under the curve, but above the interval. So we're interested in that area there. You can call it capital A if you like. And the idea is to say, all right, I know how to do this. Let's break the interval from A to B up into a gazillion little pieces. Floating above each of those little pieces is a rectangle. The height of the rectangle is given by the curve. Looks like I'm using right endpoints in this drawing. This goes on and on and on until you get to the last few of them, like so. And the area is nothing other than the limit of the sums of the areas of those rectangles as the number of rectangles goes to infinity. This is a Riemann sum from back in the day. And in the end, we find out that the area is nothing other than an integral. Where the right-hand side of the equal sign, that's just pixels on a screen. It's just the shape of the notation we use to stand for that limit of Riemann sums process. And most reasonably well-behaved functions, that limit of Riemann sums exists and comes out to something meaningful, and that's what we declare the area to be. Okay, Let's ramp it up. So in chapter 15, I guess we're going to do this. Not a curve anymore, but rather a surface, z equals f of xy. Happening not in 2D space anymore, but rather in 3D. So say like this, x, y, z. The graph of our function floats not above a closed interval from a to b anymore. This time, floats above a closed rectangle. The closed rectangle occupies space in the xy plane from x running a to b, say. So let's get the x's in green. So x runs a to b, and let's get the y's in red. And y runs, say, c to d. And so this region is a rectangle, boundary included, flat down there in the xy plane. And we are interested no longer in the area under the curve, but rather the volume under the surface. The move is the same. Let's break the region of integration into a gazillion pieces, which for us now means a bunch of little rectangles in a grid like that. And floating above each little rectangle, we have not a rectangle like we did back in Calc 2, but rather a column or a pillar or whatever you want to call it. The top of the column is governed by the surface. The base of the column sits in that one little piece of that patchwork. So there are columns all throughout the entire picture. Some are tall, some are short. But if you add up the individual volumes of all those columns, you will get the total volume under the surface. And therefore, we declare the total volume under the surface to be, all right, and now you need some pixels on a screen. Here is the symbol. We call this the double integral of the function f of xy with respect to area over the region R. So that R notation underneath the double integral, that means the rectangle over which we're doing the integral. And that double integral is nothing other than a Riemann sum also. You take the limit as n goes to infinity and as m goes to infinity, where n and m are the number of pieces you're breaking AB into and CD into. You find out the total volume for each little grid that you might be able to put on that rectangular region, and you take the limit as the grid gets finer and finer and finer. If the function is continuous, for example, that limit will exist and come out to something meaningful. And that's what we mean when we say the volume under the surface. So those are the two pictures, Calc 2 versus Chapter 15. Now you can imagine drawing anything substantive in one dimension higher seems like a tall order. But analytically, maybe there's such a thing as triple integrals, quadruple integrals, quintuple integrals. So we're going to focus our heuristic reasoning on the two-variable situation, but all the while, we'll keep our eyes peeled for the natural generalizations into higher dimensions. For now, though, just two variables. Now, the beauty of the new picture, which I'm going to draw bigger here, is that computing the double integrals might be a matter of Calc 2 only. So there's a surface, z equals f of xy. This is our new normal. So all our pictures look like this. And we're imagining that surface as floating above some kind of a rectangle. In the xy plane, say like this. So the region of integration, that's all this down here. And if we're interested in the volume under that surface and above this rectangular region, again, call it R, we can actually turn it into two Calc 2 problems in a row. And here's the sense in which we can do that. Imagine a collection of guillotine slices in green, where the slices are in the pure x direction. So there's a slice, here's a slice, you have all these slices in green in the pure x direction. Each of those has some kind of area. So if I shade this slice in, that has some sort of two-dimensional area. And if we shade this slice in, that has some two-dimensional area. And if we shade this slice in, that has some two-dimensional area. Now, each of those areas we could compute with a good old-fashioned integral. And then we could add up all of those areas as if they were laminated together left to right. And that would give us the total volume, as if you glued together all those little thin slices. That would give you the total volume underneath. Thus, the way we actually compute the double integral over the region R for the function f of xy with respect to area is often as what's called an iterated integral, which is two integrals back to back. The first one is done with respect to one of the variables. The other is done with respect to the other variable. Now think about those green slices. Each of those green slices is at a certain x. And at that x, to figure out that area, you would do old school Calc 2. In other words, break that one slice into a bunch of rectangles. So those rectangles are for x values running, say, a to b. So for x running a to b, we're integrating f of x, y. On that one slice, y is constant. This is y on that one slice. X is changing from a to b. So since these are x limits of integration, this integral must be done dx. And inside the parentheses, what you have is the area of that one slice. And then you're going to add up all those slices from c to d. And that outer integral is done with respect to y, because the quantity inside the parentheses depends just on y. For each y value, you will get some area. You could even call it, if you wanted, area depending on y. So this quantity inside the parentheses is the area of that one slice at location y. And you have an answer for each slice at each y between c and d. So on this picture, that's A, that's B, this is C, and this is D. So x varies A to B, y varies C to D. Moreover, if on this picture we had drawn the guillotine slices in the pure y direction, and then laminated all those together, not left to right, but back to front, we'd get the same volume, so we expect that that iterated integral is the same as if we had done it in the other order. This time the inside integral is done with respect to y, and the outside integral is done with respect to x. And the fact that those three quantities are all equal is called Foucaults Theorem. So this in the box is essentially this result called Foucaults Theorem. The hypothesis that your book uses for the first version of Foucaults theorem is just that the function is continuous. So the point is this: as you do problems in section 15.1, you will be asked to compute double integrals. But to compute those double integrals, you will simply do two integrals back to back. The inside integral will be done with respect to x. Think of it as like the flip side of partial differentiation. Do that inside integral in this line with respect to x. Treat y as constant. Then, once you're done with the inside integral, you will have some expression that still has y's in it, but no longer has x's in it. And then do that integral from c to d, or the other way around. And you will find, actually, sometimes the order dx dy is superior to the order dy dx. Sometimes dx dy is inferior to dy dx. A lot of the time, it's kind of 6 of one, half dozen of another. It depends on the problem. But Foucaults theorem is great because it means you get to choose the order. You want to go dx dy, or do you want to go dy dx? All right, that's it for 15.1. Get in there and start computing some integrals. See you next time. Bye.